Hi, Stuart here. Today we're going to talk about a pattern for processing a lot of messages reliably. I've nicknamed it Scatter-Gather-Munge. The scatter part obviously is the ocean of messages coming to us. The gather part is collecting them, and the munging part is doing something with them. Kind of the problem statement is we need a pattern to deal with lots and lots of messages. And this can be from telemetry, it can be from manufacturing, it can be from your supply chain, whatever. But, we need a way of getting those messages in reliably and extracting analytics and data out of them. And we need to understand that messaging needs are going to change over time, so we want something fairly, malleable, fungible, but we don't want to be in a position where we have data sourced ourselves into a corner. So there's some basic enterprise patterns, some of which have been talked about in my prior videos, but I'm going to revisit the ones now that have to do with this domain specifically, and that is the processing at all stages should be reentrant. And that is, no matter how many times I process a message, the same message, it should have the same output, the same results. We need to be able to process messages out of chronological order. Chronological order is rarely achievable without taking an enormous chunk out of your throughput, and also creating situations where small deviations in time can cause deadlocks or blocked processing. So it's really an anathema just in general. Anything that sort of smells like a non-reversible transaction is an anathema at enterprise scale. Processing should be stateless. The state is the message, and of course whatever downstream things we're putting the message into. But the processing itself should be stateless. For any particular processing block, it gets the message, does something, and then exits, and it shouldn't remember after that. And that will make, in combination with making these bits and pieces really small, that will give us really good throughput. And also very good density, because if we're going to process these kinds of messages at scale, we got to consider cost. Cost is a big deal, and the way that you can tackle cost is ensuring that you can have really good density. Density just means how many different instances of processors can I pack into the same amount of CPU, RAM, I/O, and so on, right? That's what density means. So the other thing is that processing should be resumable. So having processing be reentrant and processing be resumable are related, but they're not identical, because within a processing block, right, it could be a multi-step block, and we could get partway through it and something horrible could happen. So there's really only a couple of strategies for dealing with that. One is state inspection, which is I look at what has been done or transformed, or I'm looking at flags that I've added to the messages, and I can skip the steps that have already been done. And the other is gating. And gating is the process you need to do if, like, we're updating a database or a data store, right? It's an existential check to see, has this step been done? If so, I can skip it and go on to the next. And generally, depending on the little worker, right, you may need to use one or both of those things. The other thing is, unlike other messaging patterns I've talked about in prior videos, messages can be cloned but should never be joined, because in these kind of processing systems, those joins are A, very hard to coordinate, B, create the sorts of transactions that cause other kinds of blocking in our system. You can end up with some really weird processing states. And for a complete list of all the things that can go wrong with queue systems, I refer you to my previous videos. So the other thing is that as you clone messages, they should retain the original unique message ID, but then you should generate another ID that represents the cloned identity. Show you one possible mechanism, right? I'm not proposing that this is the absolute way to build these things. I'm just saying, having worked on 3 or 4 of these things at enormous scales, I've learned some lessons the hard way, and I'm hoping to pass on some of the yikes, don't do that stuff to all of you. We're going to talk about the various building blocks. And some of these things are components, some of these things are patterns or practices or whatever. And the first one we have to talk about is what makes a good message. Generally speaking, the more generic the message payload is, the better. This is sort of a very minimalistic one that assumes that there's only one kind of message. It assumes that the message ID and message date time fields actually came from the queuing system itself or the entry system itself, and I'll explain more about that in a bit. It assumes that the messages are capable of tracking the number of times that they've been reprocessed. At some limit, we want to go, yeah, this is never going to process. We should kick it to the curb. They should hold some sort of a history, simple or complicated, and of course message data. In this case, we're implementing it as a dictionary. If you have something more specific, then you can use something that's more nuanced than just a dictionary. A dictionary, of course, implies that each key is unique. So if you need to have repeated keys instead of a dictionary, you'd use a list of key value pairs. So you'd convert this dictionary to a list. And then you could have as many duplicates as you want. But then that induces another problem, and that is, what do you do when you have duplicate properties? Are they all ANDed together? Is the last one the right one, or whatever? And sometimes duplicate properties are desirable, right? Because there could be a whole bunch of different, for example, tags that you could add. And we could have a tags field that's separate so that we could build out a tag cloud or select messages by tags or whatever. But it just depends on your scenario. So this is not for sure a super baked thing. This is just my little example that I knocked out in a few minutes, reviewing in my head some of the things we built before. Spend a lot of time talking about the pros and cons of the message design. And probably the most important part of the message design is, how am I going to convey different payloads with different semantic meanings over time? Like, how am I going to express the kind of message and the variance in the message data? Because that will turn out to be really important later. It's really hard to retrofit messages, especially if your collection apparatus is now baked into, say, hardware that you've distributed all over the world. It's just not going to be a doable thing. Getting people to update their BIOS or their operating system or their whatever, even the little client pieces, is super hard. And you're going to have a bunch of infidelity, which is basically people who can't or won't upgrade. And so you need to make your message formats as generic as possible, but weighing the usability of that for people who are trying to create messages. Because the chances that the team that is designing this part of the system, right, the cloud part, and the people who are going to be implementing the embedded hardware, the plugin, the driver, the whatever, is that they're going to be the same team, are almost zero. So you wanted to spend a lot of time talking to those people, getting their use cases, what kind of data are you capable of transforming? And then, how big is it? Because big, bloaty messages are tough to deal with when you're getting, tens of millions, hundreds of millions, billions of them an hour. If you're going to invest in anything, invest in time in your message design, because you can fix almost anything else with different levels of pain later. But once you give a message contract to the people who are writing the stuff on the client, you got to kind of live with it, because changing it's going to be super painful for them. And it may not even be possible, right? If it's flashed into a device and that device is not super accessible by you. A lot of IoT scenarios are like that, surprisingly, where you pushing new bits to the client aren't always the easiest thing in the world. And it's fraught with danger, right? Because, something goes wrong and now you can't talk to that device anymore. That's not happy making. So invest. The other thing is, any queuing system you plan to use has to implement leasing in some form. Now, the good news is All four of the big four enterprise queuing systems all have leasing. The one I've used the most is Azure Service Bus, but Kafka and some of the other, big time messaging systems all have some flavor variant on leasing. What does leasing mean? It means when I dequeue a message as a worker, I have a certain amount of time to process that message one way or the other, and we'll talk about the alternatives in a second, or I lose my lease on that message and the message that I dequeued will go back on the queue, typically with some delay built in. So while I have the message, there's a clock running, right, that says you have 15 seconds to process this message. By the way, 15 seconds is an eternity in computing, right? And at the end, I am obliged to tell the queuing engine the disposition. And the three dispositions generically, right, because they're going to be called different things in RabbitMQ than Azure Service Bus than Kafka, are rejected, which means the message is never going to be processable under any circumstance. The message is in a bad format, it's evil, it's just unprocessable, not just right now, but forever. So messages that you reject typically go to something that smells like a dead letter queue. And then the two sort of happy path things are ACK and NACK. So ACK means I successfully did the process that the message demanded, and you can mark that message as don't dequeue it again, and when its lifetime expires, get rid of it. Or it's eligible to be garbage collected or archived or whatever you've set the queuing engine to do. But, don't serve this message up to anybody else. I got it. NACK means I was trying to process this message. Truly I was. But during my processing, I hit a snag, typically of a transitory nature. Like I couldn't make a connection to the database or Valkey or whatever, right? And so what I'm saying is the message is good. I just couldn't deal with it right now this minute. Please queue it back up. Typically, when you NACK something, you have the ability to enrich that message with some information, which will come in useful later. But what you're saying is I have a transient fault and I want you to queue up the message and process it some future time. Can't overemphasize how important leasing is for not losing units of work, for durability. If your messaging system doesn't support some flavor of leasing, and again, all the big ones do, stop. You just are not going to be able to have a system that is reliable and trustworthy by the business. You're just done like dinner. You need to find a new queuing tech. And again, there's a ton of good ones out there. I've queued my message. I get partway through my message processing, and I decide I can't process the message. I have a transitory fault. Generally, I can't get to my database or my whatever. But it's, it's temporary because we're going to build systems that are self-healing or maybe just the SQL Server is too busy right now or whatever. So the recovery process is I want to increment the number of retries. I want to compute the earliest dequeue time. We'll talk about that in a minute. We want to add a history record that says, why, what was the root cause? Like the SQL Server is too busy or I got an error from Valkey or whatever. That is the recovery process in the yellow box. And then the message is enriched at this point with that information. And then when you NACK it and put it back on the queue, you're actually updating the message on the queue. Under the covers, this sometimes results in a brand new message because messages are immutable in your queuing system. So you're actually dropping the old message and adding a replacement message. And as long as the NACK succeeded, that's a happy making thing. If the NACK actually fails, the leasing thing will kick in automatically, right, and correct that. And then it'll just get reprocessed again. And hopefully then this time, if there's still a transitory fault, the recovery process with message enrichment will work and the NACK will succeed and the enriched message will take the place of the old message. Most of the big queuing systems have a way of doing this. So the question is, well, the rubric is we shouldn't just requeue this message up with the original processing date. Enterprise queuing systems invariably have a date time field of some variety. Could be an offset, it could be a time span, it could be a date time, it could be whatever your thing is. What you want to do is make sure that you compute a time period that's longer than now, and we want to implement exponential backoff as well. So we're going to use the number of retries as our exponent, and we're going to have constant. We'll show you the algorithm, one possible algorithm a little bit later. Why are we backing off? Well, the first time we back off, we don't back off for very long. Maybe because we're hoping the transient fault that caused us to not be able to process the message was very transient indeed. Subsequent retries get longer and longer, and so further and further away from now into the future. And that's to ensure that the message becomes processable, that the system that was causing it to have a transient fault has healed itself. So we want to do exponential retry, and we want to make sure that we always queue up messages into the future. So don't deliver until sorts of date fields. And again, depending on your technology, I promise you there's some field to achieve that. And so here is a not uncommon formula in C#. We compute a delay, which is using the number of retries as the exponent and a number of base seconds. And then we say, okay, well, we want to do a jitter of that. So we want to, add a random amount, usually 10% of the delay. Why 10%? It's just a back of the envelope thing that seems to have worked on all the projects I've ever done it on. 5% or 1% was too aggressive, and 10% was pretty reasonable. 20% was way too much. It's just the back of the envelope thing it's worked for me. I'm sure if I did enough math, I could figure it out exactly, but I'm not gonna because I'm a pragmatist and this works. So then we use a random number generator. Why use a secure random number generator for this particular application? It's not because we need the security. It's because secure random number generators are weirdly better at being random than pseudo random number generators, which is sort of the default for most programming languages. So random in .NET. Whereas secure random is more expensive computationally, but if you were to plot a distribution of all the numbers that came out of secure random.next or versus random.next, and you did 100,000 of them or 1,000,000 of them, and you plotted them against the same range, in this case 0 to jitter max, what you would find is the secure random pattern, if you run that over and over and over again, will jump around a lot more than the pseudo-random one. The pseudo-random one tends to produce the same trends over and over. You can spike that a little bit by giving them different seeds, but you can avoid the entire problem by using a secure random number generator. And typically the number of clock cycles that costs you is minimal because these days computing equipment has crypto chips in it, or it has support for it in the hardware, and the programming language detects the hardware and goes, at runtime and goes, I'm going to use that. And then you end up with a delay, and the delay is in seconds. And then, depending on, again, whether or not your field is a time span or an absolute date time or whatever, you can then use that delay and add it to what time it is now. Happy reminder, if you're geo-distributed or ever will be geo-distributed, or you suspect that someday you might ever be geo-distributed, you always use UTC. In fact, just always use UTC in the middle tier period. Topics. Depending on your queuing technology, this may have a bunch of different names. But the upshot of this is that as things are queued up, that the topic has a whole bunch of different subscriptions, and each subscription gets a copy of the message. And in fact, the subscription is actually usually some sort of dynamic algorithm. It's virtual. And what makes it virtual is every subscription's got a rule where the simplest rule is 1 equals 1. Well, so give me a copy of all the messages. But you can do things like look in the message body, look in the message header, and most queuing systems have reasonably rich set of functions or inequalities that you can run. And the upshot is if the result of that computation is true, the subscription gets that message, and if it's not, the subscription does not get that message. Easy peasy lemon squeezy. And what that allows you to do is, for the same message queuing instant, you can dequeue things for different consumers. So, consumer 1 is just storing the messages to storage. Consumer 2 is trying to compute some dynamic statistics or counts or whatever. Consumer 3 is passing it on to the pipeline that will do more nuanced analysis or what have you. But subscriptions are freaking brilliant, because it turns out that for all of the major queuing systems, because they're fundamentally virtual, they're very, very efficient. But that also explains why when you ACK a message, that the message doesn't go away, because not all the subscriptions may have processed it yet. So now these subscriptions are able to process messages in their own time. So if consumer 2 goes down for a little while, or because we're updating it or maintenance or whatever, the consumer 1 and consumer 3 will happily motor along, but consumer 2 won't lose its messages if the message retention time is greater than the amount of time that consumer 2 is down. So in enterprise systems, we typically set the message retention, unless it's completely impractical, to a week, 2 weeks, a month. And then as we run the system, we figure out, what's the actual dwell time through all of our consumers, and we can start cranking that retention level down, and that makes our queuing part more efficient, usually costs less, but it's going to be a lot more efficient generally when you start, just crank it up to the max for no other reason than debugging. And then, you can tune the retention. So just remember that knacking a message doesn't get rid of it, which is why another reason you want to use leasing. Because if you aren't using leasing and you dequeue a message, it is gone forever. If you're going to have subscriptions, you want to make sure that the subscriptions have the opportunity to process the message. So you want something with message retention, and you want messages to not go away. I've seen interesting implementations where people mix and match those things and then don't understand why their messaging system isn't stable. We talked about, that subscriptions are fundamentally virtual with Boolean expressions. A couple of things you want to do, and they're a little mathy, but they're not, super hard mathy. If you have a scenario where something needs to go to subscription P or subscription Q, but never both, make sure that the Boolean expressions that you build as the rule on that subscription are really mutually exclusive. And of course, you can do that by just feeding through a bunch of data and making sure that it only goes to A or B, or you can use De Morgan's laws and verify for yourself that the expressions are mutually exclusive, which means that if you ever decide to change the expression on mutually exclusive subscriptions, you want to do a lot of testing before you roll those into production, or weird things will happen. I'm going to use some terminology. Other people use other things, but this is kind of how I talk. I think about processing in slices. In the same way that as an architect, when I want to demonstrate something to the developers and designers and UIers and whatever, I build a vertical slice through the entire architecture as a demo and go, this is kind of the ideas that we want. And then people can run it on their own, desktops, and they can fiddle with it and they can dive into it and figure it out. So for me, a slice is just the minimum processing end to end. And the caveat I'll put here is that typically the team doing analytics is the team that your team is delivering data to. I typically exclude that in my slice because our job is to deliver data to them, and what they do with it is their business. So I typically leave that out of the slice. Scale is the mechanism by which we take the minimum components in a slice and we scale is the mechanism by which we scale slices. And so for individual components in a slice, we can scale them up, we can scale them down, but we can also replicate the slices. So if you need to have geo distribution, you're going to have slices all over the world. or wherever you need to have them. So you may only be servicing the European Union and the UK. So you might have, 4 data centers in your mix, and each data center has one or more instances of each slice, and each slice's components are scaled up or out to meet the message volume going through your system. So a couple of takeaway patterns. Again, each component should do as few things as possible. You want to dispose of bad messages early, because if you can reject messages early for being malformed into the dead letter queue, and then you can have a different process that looks at those and goes, wow, half of our messages are being ash canned. That's no bueno. But, that's an aside, but an important thing to implement. Like, don't ignore the dead letters. And then we want to complete messages for which you only need metrics early. If we're only counting something, so we can generate messages like how many per time, we want to process those messages and act them to get rid of them. And then if there are messages with more juicy payloads, they're not competing with bad messages or messages that are only used for metrics. And instead, you can focus the rest of your messaging pipeline, the rest of your slice, on transforming the messages in ways that are useful to the analytics team. Remember, our goal is reliably receive messages without losing them or without blocking messages from coming in, and delivering them to the analytic team. So we're responsible for the bit in the middle. So here's a slice architecture. Geo-routing. In other words, for a particular client, what data center should their messages flow to? And I'll give you a little bit of a warning. Notice it's got the infrastructure symbol attached to it, because this is something you shouldn't code yourself. Someone else has solved this problem already, way better than you ever could. Go talk to your networky people for your cloud or your data centers or whatever, and they will help you set up geo-routing, which essentially is how, for this client, where do its messages go? The other thing that you want to make sure happens is that the geo-routing system does 2 things. One is, it never gives somebody the address to an endpoint in a data center that isn't currently working, right? That's not good, because we're going to not be able to get messages. But the other thing it should do is it should periodically expire the advice it gives. So if I'm a client and I pull down the data center selection stuff, like what's the URL and other things, sometimes it hands out auth tickets, whatever. What I want to make sure that happens is that data is cached for only a certain duration. And the duration is a function of your stability. But the other thing is that the client should be smart enough that if that fails enough times, it should recall the geographic routing endpoint and get new stuff. A, the stuff on the client should expire, and B, a geographic routing system should never give somebody something that won't work. It may be suboptimal in terms of, the least cost routing across the network, but at least there'll be a place to deliver messages to. Then in each data center, you want to have that data center be part of a cross data center firewall. And that may or may not be the same appliance as your geographic routing, but examples of this are Imperva Encapsula, Front Door, other things like that. So things that are capable of getting metadata about the origin of the messages and whether or not that origin is evil or not, or whether or not you're being spammed with messages from a place you shouldn't be getting from. So cross-center data center firewalls provide DDoS and geofencing, and they can do basic message inspection. So if it's, if you say, well, my message format's always going to be JSON and it doesn't look like valid JSON, the cross data center firewall never even delivers the message to your data set. And it goes into a separate log. And again, don't ignore those. And don't ignore the logs on your geographic router either. But typically, your networking team is monitoring that. And if they see something funkadelic, they'll tell you about it. The geofencing is interesting in the sense that to some degree, it is a little redundant for geographic routing. However, there are attacks where The geographic routing is really very, very basic. It just says, well, you're in Europe, your least cost travel time is here, but the messages are actually being reflected through some sort of a proxy. And the cross data center firewall is much more equipped to do traverse inspection, or, how did the message come to you? And make decisions that, in fact, the real origin is somewhere evil and needs to be stopped. So then in each data center, you want highly available load balances. And these top 3 layers, they're labeled with the infrastructure icon because you're crazy if you write these yourself. There's so many good products out there that can do this. If you're running this on a cloud, the cloud provider almost always has a really burly version of this. You don't have to write it yourself. So really, your responsibility is the slice. Whatever your entry is, we want it to do some basic stuff. We want it to do some more message inspection, even more granular than the cross data center firewall did. So now we're not just saying, is this payload JSON? We're saying, and is the encoding of this payload okay? We're actually validating the elements in it and so on. We want to make sure that we are, sort of distributing messages to the right entry queue. So the entry queue is defined as being the first enterprise queue any message drops on. But you can have different queues for different purposes. So messages of type A go on to queues 1, 2, 3, and 4. Messages of type B go on to 5, 6, 7, 8, or whatever. But that's the sort of work you want to do in the slice directory. And then the basic component is you have, one or more queues on one or more instances of your queuing engine, one or more subscriptions that go to different data processing pipelines, as we talked before. And some of those are going to make decisions and then re-queue the message, maybe transform, maybe not, onto a different queue that's inside, and so on and so forth. Other subscriptions will do things like generate fast metrics, and they can just do that in one pass, like if it's doing a count or something. This is the overall architecture. And the general rule of thumb, as I said before, is if there's an appliance, a piece of hardware, a third-party system that does the job, use it. Write as little code as you can. So here's a top-level checklist for these kinds of projects. On the left, we have the famous list of 10 that my friends and I came up with. These describe all of the non-functional requirements that are possible. And they're really non-functional requirement categories. So we just try to get the number of categories down to 10. And then here are some special concern areas for 5 of the non-functional requirements categories. And so we want to make sure that we understand the monitoring the failure of any of the processes and why they failed. We want to manage the versions of not only the messages, but of the components. We want to make sure that we are getting the throughput the business requires. And ideally, the less time the message spends in the entry queue, the better. We want to make sure that we understand the lossiness of the system, so how many messages are being abandoned. And in order to do that, we're going to have to go all the way up to the top layer and ask things like the global distribution system, like how many things was it outright tossing? And we'd have to go to our distributed firewall and say, how many things did you toss because you didn't like their origin, and so on. And then, for security, identity and access management, DDoS protection, which again, you should not write yourself. You should have it be done by the appliance. How many things are getting rejected because they're malformed? And then how many messages are inauthentic? Inauthentic messages are super hard to figure out. But generally speaking, they're relatively rare because the value proposition to a hacker to make inauthentic messages is a lot less valuable than just making you miserable by launching a DDoS attack that your hopefully infrastructure will handle. And then you have to understand how much this thing costs and what are the value of the results to the business. And you want to make sure the value exceeds the cost. And you also want to make sure that you've built troubleshooting into it end to end. So these are just some things that we call out when we're doing the requirements analysis on these systems above and beyond the normal questions we ask of the 10. My name's Stuart. Thank you for your kind attention.